So thanks very much for the invitation, and I really have no business being here. I've never been on an FRB paper, never done anything with FRBs. There's no figures from FRB papers in this talk whatsoever, but I have played a role in the origin story of understanding another type of fast transient short gamma ray burst. So I wanted to use those lessons learned, draw from that field, and I came up with 10. I had 5 that I came up with on the plane here, and then yesterday scrambled to rewrite my talk based on all the new results. And so as I worked later into the night, they became more philosophical in nature. So here we go. I don't know if any of this will be useful or not, but okay. So I was just thinking overall, just from 12.11.02 and all the discussions I heard yesterday, generally in TDA and a lot of major discoveries, the first is rarely a great prototype, so you're not alone. And I bet a lot of you have these other, your favorite example. These are just some that I could think about, from explosive transients, millisecond pulsars. Maybe 170817 will be weird. We need another one to make that comparison. And of course, 12.11.02. So I think it's important to kind of keep that type of philosophy in mind as we go forward. So that was lesson 1. Lesson 2. Annoyingly, the first few may also not be representative of the population. The best example that I have just from my own knowledge is the host galaxies of short gamma ray bursts. And so I'll just walk you through the first few and how they compare to the population that we know about today. So short gamma ray bursts, the first one that was well localized back in 2005 was coincident with a massive elliptical galaxy. So that was, I'll populate this pie chart on the right. The second with a star forming, so now we're 50-50. It's a draw as to what the progenitors are. And at this point, we had deep limits for following these first few on supernovae, so we knew they weren't coming from massive stars, but they were definitely coming from an older type of progenitor. The third one was also from an elliptical galaxy, so that's 2/3, 1/3. And the fourth one was from a galaxy cluster, probably from an elliptical galaxy, if you trust this association with galaxy B. But anyway, so it's 75-25. So at this point, we thought, okay, they're all mostly from older stellar populations. They must be, it's coincident with the very long merger timescales we expect from neutron stars, but we needed really, really old progenitors to explain this population. And no type of prompt progenitor would be sufficient. Now we've been doing our due diligence and collecting about 60 plus or so host galaxy associations, going after every single one with our best and brightest telescopes, and we now have a population of about 60 or so, and this is in prep work. And you can see there's just a rich diversity in terms of luminosity, in terms of offsets, in terms of how well localized each burst is, and generally in terms of properties. And so now the tables have really turned, and it's really the opposite from what the first 4 events were telling us, that now we have about 73 star-forming, kind of Milky Way type star-forming galaxies, not really like dwarf type or super star-forming, and only 27% are elliptical. This luckily can be accommodated with a single neutron star merger progenitor, because you can chalk it up to just long merger timescales, a wide range of merger timescales, so they can explode kind of in any galaxy you give them. The third lesson, and this is just a little bit more specific, now going a little more practical, locations have been a key diagnostic in terms of understanding the progenitors of transients. So Tarne touched on this really well. I just want to reiterate that point through a couple of examples. So this is the cumulative offset distribution of various types of transients, short gamma ray bursts, long gamma ray bursts, various types of supernovae, calcium-rich transients, which are really weird and thought to be high offset from older stellar environments. But you can see that there is a rich diversity, and if you can actually get sub-arcsecond localizations or even arcsecond type localizations, and you can fold that measurement uncertainty in with each localization, you can get these beautiful types of diagnostic plots. You can go a step further and actually understand if you can measure the half-light radius of the host galaxy, you can actually do host normalized offsets. So you can do this with any FRB for which you have a host association. And so here, with just the physical offsets, you can see, you might naively expect short GRBs and various types of supernovae to line up pretty well, but when you incorporate that host galaxy information, they actually immediately separate. And so you can see again that short GRBs from neutron star progenitors extend to much larger offsets overall. So these are the types of diagnostics that you can do with good localizations. And they've just been tried and true methods for understanding progenitors of other transients. Another way to do this is just the fractional flux method. So instead of actually looking at the physical offsets or the host normalized offsets, you actually take into account the galaxy light, and so the distribution of galaxy light. And so this actually is a great method for kind of galaxies with irregular morphologies and to put everything on an even playing field. So in this diagram, I'll populate this. This is a cumulative distribution versus fractional flux, and all you need to know is that values of 1 mean that the transient is on the brightest pixel of the host galaxy, and anything up here, values of 0 are on the faintest values. So basically a population over here would be strongly correlated, and then up there would be weakly correlated. So some of you may have seen this before, but long gamma ray bursts, core collapse supernovae that come from massive star progenitors, they trace their host light very well. These studies were generally done in the G band or rest frame UV. So you can see that's commensurate with their very massive star progenitors. And then older kind of thermonuclear supernovae, as well as short gamma ray bursts from older stellar progenitors, actually you can see are in the opposite part of the diagram. And you can even do this by splitting into optical and near infrared to get those diagnostics. If you have a large enough sample of well-localized events, you can even, and this has been done for supernovae, apply the same method but split into supernova subtypes. So from thermonuclear to supernova 2s, 1Bs, 1Cs, various types of stripped envelope supernovae. So you can actually apply the same type of method. And this was done in H alpha, so you can really pinpoint, how well correlated are these with the H alpha light or the star formation of that host. And so I would say that, this has been a tried and true method in terms of understanding the locations and the progenitors of other types of transients, and that you have some of this information at your fingertips for those well-localized events, or you should go get HST time to do this type of precise analysis, as it's been really useful for our understanding of short gamma ray bursts, for instance. Okay, lesson 4. Search far and wide for the smoking gun. I don't have to tell this audience, that I know many people are thinking about, what could be a smoking gun for the progenitor or progenitors of FRBs. And so I just was thinking about this. We had to wait for the LIGO detection to really get that smoking gun for short gamma ray burst progenitors. But before that, we were kind of looking for tentative smoking guns. And so one of those smoking guns was kilonova emission, which comes from the radioactive decay of heavy elements produced in the merger. And Brian is credited with popularizing this. But 8 years after the first afterglow detections in short gamma ray bursts in March 2013, Jennifer Barnes and Dan Kaysen told us that these could potentially be red, or that they peak in the near infrared band. This was 8 years after the first detections. A lot of our searches by necessity had been done in the optical. And then 3 months later, it turns out that the first near infrared excess was actually detected and interpreted as a kilonova. And so this is just a snapshot of short gamma ray burst location, and you can see there's a clear excess in the infrared. And this is just a light curve version of that figure. Of course, this was what I'd say a tentative smoking gun because we didn't have a spectrum like we do for 17817, but this really kind of changed the field. Having that model in place and then being able to adapt our observing strategy there, I think, was really important. Okay, 5. When at first you don't see anything, try again, especially when it's to look for magnetars. I thought that this audience would appreciate that. And so this is just some recent ongoing work that we've been doing to look for magnetars at the locations of low redshift short gamma ray bursts at late time, so 3 to 13 year timescales or so. And basically, the idea is that if a hypermassive neutron star remnant is created that gets highly has acquired magnetic fields, high magnetic fields through the merger process, it can impart some of that spin down energy into the environment, accelerate the ejecta around it, and create this slow synchrotron shock. So that's these kind of simple analytical models that you see. And these recent observations actually just finished reducing last week with the VLA, and we can actually place quite deep constraints depending on kind of the rotational energy and the ejecta mass you assume. If you dial down the rotational energy a little bit, of course, your limits become less constraining, but suffice it to say that we've been able to at least place some constraints. And there's no persistent radio sources at these positions. Okay, so now I'm transitioning a little bit more philosophical, I think. In the era of low event rates, dedicated follow-up by these island groups, which have, by the way, been really beautiful efforts, ensures comprehensive follow-up of a limited number of exciting events. But, to be honest, as event rates increase, the strategy, I don't think, will be the way to ensure the advancement of the field. And I think this is something that, we should be thinking about. One of the byproducts of this is that actually this kind of can introduce bias in terms of the type of events that we follow up. And so this has been made clear both in transient surveys, where untargeted transient surveys give you a stream of data, and then you try to choose which ones to spectroscopically follow up. And those have been, issues that transient surveys have had to deal with. This is my own personal example where this is 15 years of host galaxy characterization for short gamma ray bursts. This is just a histogram. Recently, we've been trying to follow up every single one, actually going back and trying to redo certain redshifts, and we're starting to see kind of a growing population of after a few years of following these events, of kind of more high redshift ones, and really filling out this higher end of the redshift distribution. So basically, the idea is that, the more kind of open information that we have, the more that the community can ensure that every single event is followed up and not the ostensibly less exciting events are left behind. Okay, lesson 7. It's useful to revisit host galaxy associations. So I thought I threw this in after seeing some of the photos from yesterday. But this is essentially the position of a gamma ray burst. You can see from ground-based imaging, there's nothing there. G1 is really the only potential galaxy in town. For gamma ray bursts, we actually don't have the advantage of having a position from the afterglow itself. Just, FRBs, you at least have a kind of a measurement from the DM, or at least an idea. For us, we don't actually really have any indication, at least for short gamma ray bursts. So we went and looked at it with HST, and sure enough, right at the position, there's a galaxy right there. And so that can actually, basically from ground-based imaging alone, this was not sufficient to actually make the right host galaxy association. And this is not super common, but it definitely incorporating these bursts in is really important to our sample and understanding. If you didn't believe it, I had a zoomed in picture. This is another, let's see how many, okay, I'm gonna skip this. Okay, looking forward, we should be thinking about capabilities and potentially dedicated follow-up facilities. I think some of these questions will be coming up in the discussion, but just in the era of kind of large data stream, large amounts of data, large numbers of FRBs coming in and being made available, we should think about kind of what future facilities would be able to handle that. Okay. I promised philosophy. Information is oxygen. Please share it to keep breathing it life into the field. So I'm actually pretty jealous that the FRB community just has so much information, even from the pulse itself and from the polarization, just the immediate information that you can get just from the actual initial signal, let alone the host galaxy properties that localizations provide. And so I think just this, I'm really excited to see kind of what correlations arise, if any, between these various properties so that we can understand more about the progenitors. And please share this information if you have it. It helps the field. And then a final musing on discovery. And this was actually, I had a conversation with Dale Frail a couple months ago, and he pointed me to this poem. We were just talking about discovery in general. So I thought I'd share it with you. This is about a poem that Longfellow wrote just about how the sky looks different, or the universe looks different in moonlight. And so this is the last verse of it. In vain we look, in vain uplift our eyes to heaven if we are blind. We see what we have the gift of seeing, what we bring we find. So essentially, if you don't read, if you don't interpret poems well, if we can't set aside our biases, we'll find what we're looking for. Okay, these are my 10 lessons, and I will stop. Thanks.